Hello, welcome to section 6.1. We're going to talk about how to solve systems of equations by graphing and by a method called substitution. So throughout this video we'll talk about what a system of equations is, the different forms of linear equations like slope-intercept form and standard form. There's a couple definitions like if a system is inconsistent or consistent, and that will depend on how many solutions the system has. So we'll start by just doing a fairly simple problem where we're just going to have two lines that'll crisscross, and we're going to find the intersection of those lines. Both of these equations are in slope-intercept form, so that makes them pretty simple to graph. So what I'm going to do is identify what the slope and the y-intercept are in each of these cases and just graph these. So for this first line, your slope is the coefficient to x, so it's going to be 4 over 1. And my y-intercept is going to be 3, so that's going to be where our function crosses the y-axis. For our other equation then down here, notice we have a negative x, so that means your slope will be negative 1 over 1. And your y-intercept for that will be negative 2, which means that'll cross the y-axis at negative 2. So I'll stick with the two colors here. I'm going to start with this top one, and we're going to go up 3 for the y-intercept. Now, if I go up 4 and over 1, I'm going to be off the graph. So that's okay, but I want you to understand I can also go down 4 into the left one. So you can either go up 4 into the right one, or if it's a negative and a negative, you'd be able to go down 4 into the left one. So I'm going to do that a couple of times, just enough to get a line through here. So what I'm going to do is grab this line tool and draw a straight line going through. And then I'm going to graph the other one, which is going to start at negative 2. And this one is going to go down 1 into the right one. So it'll be negative 1 is the down one, and the positive 1 is to the right. Or if I would have taken the negative sign and attached it with the bottom, you'd be able to go up 1 and then to the left one. So you'll see where the intersection of the two lines is. And that's going to represent what our solution is. So at the very end of all of these problems throughout this entire chapter, you're really focused on this point right here. That is the solution to both, that's the solution to the system. So our solution in this case is this coordinate, which is negative 1, negative 1. So let me show you why it's a solution, and then we'll talk about what consistent and inconsistent means. So first of all, this is a solution because if you think about every one of the points, so pick a line. Pick this line where my cursor is. If I were to pick every single point on that line, if you were to take an x value and substitute the x value in your equation, you would get the corresponding y value, which tells you where the point is. So every one of these, each one of these lines contains, an infinite number of points. But there is only one point that both of these lines have in common, and that's negative 1, negative 1. So we can check this in both of our equations by substituting this part in for x and then this part in for y. So I'll show you how to do that. What I'm going to do is take the left side of the equation and put the negative 1 there, and that equals 4 times the x value, which is negative 1 plus 3. So if I want to check this, just do a little algebra, and you end up with negative 1 equals negative 4 plus 3, which is negative 1. So what that tells you is that this point is on this top line. So if I want to check if it's on the bottom line, I'm going to take the bottom equation and substitute the same coordinate in. So negative times negative 1 minus 2. So this is the bottom equation then, which you're going to end up with negative 1 equals 1 minus 2, which is also negative 1. So like I said, this intersection point really is out of all of the points on both of these lines, it's the only point that satisfies both equations. And that's what's going to be called a consistent system. So let me kind of go into that on the next slide. I'll show you the three types of systems that we're going to be dealing with, and we'll start by doing the graphing, and then we'll roll into substitution, and then eventually we'll learn another one called linear combinations, which is also just called elimination. So the first example I'm going to show you, or first two examples, are going to be called consistent systems, and then I will save this one for being the inconsistent one, and I'll show you what it means. Consistent systems have a solution. So I'm going to put that down there. Have a solution. And what that's going to look like is if I have two lines that crisscross, and here's your intersection, or if you have one line and you draw another line that has the same exact equation, and I draw it right on top, if you have one line on top of another, every time you pick a point, it's going to be a part of both lines. So this is going to be a case where there is infinitely many solutions. And if a system is consistent, it means that it has a solution. So if it has an infinite number of solutions, it still is consistent. It's just kind of a freaky case. And this is where, again, you would have one line on top of itself. So you have two equations which represent the same line. It means they have the same slope and the same y-intercept. So if I were to graph both of these lines, you'd be starting on the y-intercept and moving in the direction of the slope, and it would be one line on top of another. If I were to kind of flip that logic a little bit, let's say I have two lines that have the same slope, but if they have different y-intercepts. So two lines that are going to have the same slope, but they're never going to touch each other. Well, that's a case where those are looking like train tracks. These are parallel lines, and that means we'll have no solution. And if you don't have a solution, that would mean it's an inconsistent system. So that's going to be our parallel lines, where you're going to have the same slope and different y-intercepts. So if I were to kind of backtrack to that first example, then since we have a solution, this is what would be called consistent. So if you have a solution, it's consistent. If you have infinitely many solutions, it still is consistent because you still have a solution. So the only case when you have an inconsistent system is if you have two parallel lines. So I'll move into another example, two equations in slope-intercept form. I'm going to take the top one and identify my two key pieces of information, the slope and the y-intercept. My slope is the coefficient to x, -1/2. My y-intercept is -1. I'm going to go ahead and just graph that right away by starting down 1 on the y-axis and going down 1 and to the right 2. Or I can also go up 1 and to the left 2. It represents the same slope for both of that. So what I'm going to do is connect the dots. That was really ugly, so I'm going to grab this line and fix that. Okay, that's slightly better. And then the other one, my slope of this line is going to be 1/4. And my y-intercept will be -4. So this one's going to start down here. I'm going to go up 1 and to the right 4. I could also go down 1 and to the left 4. And it's the same thing. So what I'm going to do is connect these dots. And you'll see again, I have a really pretty solution here. Both the points, both of the lines crisscrossed at that intersection. So 1, 2, 3/4 and down 3. So this coordinate is 4, -3, and that is our solution to our consistent system. So since we have a solution, it is consistent, and that is the answer. Next one. So this will be the last of the examples for graphing. I'm going to identify that my slope here is going to be -2/1, and I have a y-intercept of +2. And what you'll see for the one below it is that my slope is also -2/1, but my y-intercept is -2. So this is an example where you're going to have the same slope but different y-intercepts. So we'll take a look at what this is going to be. I'm sure you're already imagining in your head what the answer is. So I'm starting up 2. My slope is going down 2 and over 1. So I'm going to, or I could go up 2 into the left 1. So I'm going to connect those dots. And then I'm going to do the other one. So this one's starting at -2. But also, the slope is going down 2 into the right 1, or up 2 into the left 1. So I would imagine, see that these two lines are not going to be crisscrossing at all. They're parallel to each other, so this is a case where we're going to have no solution. So again, I had the same slope for both of these, but different y-intercepts, so it's no solution. They will not crisscross, which makes it an inconsistent system. That's really ugly handwriting. All right, so solving them graphically is beautiful. It's an awesome method. You're finding the slope, you're finding the y-intercept. Notice that for this example and the one at the very beginning, we had really nice, pretty intersections. So I want you to imagine when we have decimals, when we have fractions, when we have really ugly numbers, you could have two lines that are crisscrossing way the heck over here at a point where I just don't understand where that is. Maybe it's not exactly on my grid somewhere and it's between a couple points. So if that's the case, graphing is not the best method, and we need another way to do it algebraically. So here's a method called substitution. where what you're going to do is you're going to look for an equation that starts off with a y equals or an x equals. That's going to be your starting point, is to find an equation or to get an equation in that form. So you want one of your variables isolated, which means the variable is by itself. What I'm going to do is take this chunk of information here, this expression x minus 1. This is what y is equal to. So if y is equal to x minus 1, I can take that and substitute it into this top equation. So what I'm going to do is rewrite my top equation. 2x minus 3y. But instead of y, I'm going to substitute what y was equal to, which is x minus 1. And I'm going to set it equal to negative 1. So notice that I took these two equations and I had two variables, x and y. And I kind of found a way to condense it by using substitution. So now I only have one variable, which is x, and you are able to solve this. So I'm going to use the distributive property. So I have 2x, negative 3 times x is negative 3x, negative 3 times negative 1 is positive 3, and I'm going to set this equal to negative 1. Combine your like terms. I have a 2x and a negative 3x, so 2 minus 3 is negative x, plus 3 equals negative 1. I'm going to subtract 3 on both sides, and that's going to get my variable by itself. So now I have negative x equals negative 4. And then I don't like the fact that the x is negative, so I need to divide by negative 1, and a negative divided by a negative makes my x positive. And negative 4 divided by negative 1 is positive 4. So what that means is that in my solution, remember the solution is where these two lines are going to crisscross. What that means is the x part of the coordinate is 4. So if your solution to this system is going to be an intersection of two lines, you need a point. You need a whole coordinate, and I only have half the answer right now. So I need to go ahead and finish this, and I'm going to do that by substituting my 4 back in for x now. And you can do it in either equation. I'm going to do it in the bottom one. So it says y, you know what, I'll change color. So it'll be y equals, and instead of writing x minus 1, I know that x is 4, so I'm going to write 4 minus 1. So my y coordinate is going to be 3, and I can put that right here. So that means your final answer is the point 4, 3. And that is substitution. So I'll do another example or two. Looks like one more example of that. This one is slightly different. Notice in this example, both of my equations are in standard form, which means our variables are on the same side of the equal sign. So this bottom equation looks like it's going to be a lot easier to get y by itself. If I want to get this y by itself, I need to move the x over. Now since it's a negative x, I'm just going to add x to both sides. So what I end up with is y equals x plus 3. So I have this top equation, which I'm just going to actually bring down over here, is negative 3x plus 3y equals 4. So this is my system now. And what I'm going to do is use substitution. So I have a y equals the x plus 3. I'm going to take that x plus 3, and again, we're going to substitute it in for y. So I'm going to rewrite that equation as negative 3x plus 3 times x plus 3. And that equals, that looks like a y, but that's actually a 4. So let's solve this. We're going to distribute again. Negative 3x plus 3 times x is also 3x. And 3 times another 3 is 9. And that equals 4. Watch what happens here. Negative 3x plus 3x is 0. So that's going to cross out, and we have no variables left. So at the end of this, what I actually end up with is that 9 equals 4. And what you're thinking to yourself is 9 does not equal 4. So since this part is not true here, this is not true at all, 9 does not equal 4, what that means is that we have no solution. What that means is that if I were to write these two equations in slope-intercept form, one of them is, but if I were to do that to my other equation and put it in slope-intercept form, you would end up with an equation where, you would end up with a system where both of your lines have the same slope. They're going to have different y-intercepts, and it would be parallel lines. And when you have same slope, different y-intercepts, parallel lines, that is automatically a case for no solution. So you're going to know that when you're solving these problems, if you end up with something at the very end that is not true, if you end up with 9 equals 4, that is not true at all. What that means is that your system has no solution. If you were to end up with something that says 4 equals 4 or 5 equals 5, These are really good things. What that means is that these are true. That means that you would have an infinite number of solutions. So if your variable drops out, so if we have no variables left, if you end up with something that is not true, that's a no solution. If it ends up being something that is true, 4 equals 4, 5 equals 5, 6 equals 6, if you end up with something true, that would be infinitely many solutions. So I'll move on to a story problem. This is going to be one that's going to talk about the break-even point. So we're talking about a cost and a profit. So the Spanish Club is selling boxes of fruit as a fundraiser. The fruit company charges the Spanish Club $7.50 for each box of fruit and a shipping and handling fee of $100 for the entire order. The Spanish Club sells each box of fruit for $15. So I'm going to have two equations here. We're going to have a cost equation and an income equation. And I'll write both of them in y equals mx plus b form, slope-intercept form. So what I'm going to do is define that. I'm going to say x is going to be the number of boxes of fruit, and y is going to be my cost slash my income. So one of my equations will be for cost and the other one will be for income. So what I'm going to do is write them in slope-intercept form. My first equation, I'm going to do the cost one. So it's going to be y equals, so how much does it cost? It costs them $7.50 per one box, so 7.5x, plus there's a handling fee of $100. So that's how much it's going to cost to process the order. And I also need an equation to represent the income then. So when they sell them, it's going to be y equals, and however much they're selling them for, which is $15 per box. So I'm going to graph both of these lines. I'm going to start with this top one, and we're going to find basically after how many boxes are they going to be able to break even. Anything past that, they'll be making their money. If they don't sell enough at that point, they'll be losing money. So let's get a graph for these. Let's start with the y-intercept on this top one, which is 100. So this is counting by 30s, which is really ugly. So that means that right in the middle of these two numbers is going to be 105. So 100 is going to be right about here. So that's one of my points. Now I need another point on this line to graph this. So what I'm going to do is substitute a value in. Let's suppose x is 10. Let's say they sold 10 boxes. How much would that cost them? So I'm going to take 7.5 times 10, which is 75, and add 100, which means if they sold 10, or if they purchased, if the Spanish Club has 10 boxes, it's going to cost them $175. So what I'm going to do is go over to where 175 would be, and then I'm also going to meet up with where 10 boxes of fruit is, and put a point here, and then I'm going to connect the dots. So this is going to represent my cost equation. So I'm going to label this as cost, and this is my top one. Now with the bottom line, this is going to be my income. So notice that my y-intercept here is 0, which means if somebody buys 0 boxes, it's going to cost them $0. So I'm going to mark where 0, 0 goes on the graph. And let's assume they sold, let's say 10 boxes of these. So if they sell 10 boxes, how much is that going to earn them? Their income would be $150. 15 times 10 is 150. So what I'm going to do is go to where 15 meets 10 here on the line. And then I'm going to connect those two dots. So once you have those 2 points, I'm going to crisscross them right here. And we can see that we do have an intersection of 2 lines right around right here. And that's going to be where our break-even point is. So it doesn't look like it's perfect, but it looks like if they sell about 14 boxes, their cost will be lower than the income then. So what that means is that once they sell the 13 boxes it is, everything past that they will be making money. And that's what we call the break-even point. So just to kind of recap this, and we could actually solve this by substitution. So before I even recap, I'll actually show you how to do that. If this is my system here, and you wanted to solve this, I'm going to use substitution. What I'm going to do, since I have 2 y equals equations, is I'm going to take this piece right here and substitute it in for y. So what I'm really going to do is take the 15x and write it up here. So 15x equals 7.5x plus 100. And now we can solve. I'm going to subtract 7.5x on both sides. So I end up with 7.5x equals 100, and then I'm going to divide this. So 100 divided by 7.5 is going to come out to 13.3. So if they sell 13.3 boxes, so on our graph you could see it was almost 14. So if they sold the 13.3 boxes, that would be their break even. So if I take y equals, I'm going to substitute the 13.3 back in for x. So do 15 times 13.3, and that means that it would be $199.50. One sec. Yeah, so it would come out to almost $200 basically, for where their cost and their income would be the same. So again, you could express this as a coordinate, 13.3 and then 199.5. If I were to scroll back up, it looks like that could approximately be the case where this is. Again, it's not going to be exact because of the graph, but you can imagine where 200 would be between these two values. 200 would be right around here somewhere, and that does look like it's 13 boxes, and it would be about $200. So in order to have their profits exceed the cost, they would need to sell more than that amount. So again, just to recap, starting back, we talked about inconsistent and consistent equations, or systems. We solved the systems using graphing, we solved them using substitution, and then we saw what no solution looked like, and we also did a story problem.